I picked out a couple kinematic problems. They're predominantly calculus-based problems, but one of them is a challenge problem. I don't think it's super challenging, but we'll see. We'll see how it is. One of the problems at the end is a AP Physics C problem from 2005 from the free response. So we'll see if we can get there. We'll probably spend maybe 1 or 2 days on these. We'll see. So we'll do some free response ones. Maybe we'll do. Yeah, it's on. Yeah. And then we'll do maybe some multiple choice ones. We'll work out. When we feel good, then we'll move to Newton's laws. We'll do the same thing. When we feel good, we'll move to energy. You see the pattern or whatever. The acceleration of a bus, doesn't have to be a bus, it could be anything, it doesn't matter, is given by a of x of t, or ax of t, I'm sorry. So we know this is a one-dimensional acceleration in the x dimension.
The rotation
problem. Okay. It looks like a rotation problem, except if you take a look at the units, it's in meters per second cubed, which is actually really funky looking units. So that's funny. It's a little funny. So it's not a rotation problem, because if it was a rotation problem, what would the units be?
Oh, in radians.
Radians. It'd be in radians. So they're actually being kind of lazy here. They're just giving us a standard function and then saying, hey, this is some coefficient. It could be anything. They're giving it to us as alpha. It can be some number. Sometimes they'll say it's a. Sometimes they'll say it's
no correlation to the
no correlation to the rotational term alpha. I can definitely see where that's very confusing.
Wait, hold on. How is the acceleration meters per second cubed?
The acceleration is not. But the acceleration term has a coefficient in meters per second cubed, but then that t here is in seconds, so it does give me meters per second squared in the end. So if we're thinking about this big picture, he's right. This probably has a jerk in it.
Well, meters per cubed, the seconds cubed is always the jerk.
Yeah. If the bus's velocity at time t equals 1 second is 5 meters per second, what is its velocity at time t equals 2 seconds?
You can integrate in t to get 1.2 over t squared.
Okay, so
And then multiply
okay, so how do I go from from a to b? What'd you say?
integrate. Plugging in the initial condition,
Right? You agree with me?
Yeah.
So far? Now notice this is an indefinite integral.
Which means it's plus e, and then I should plug in that initial condition.
Who agrees with that?
No, over 2.
What's over 2?
A t squared.
Half.
1/2 a t squared.
Okay. Now what?
You know that the velocity at 1 second is 5, so say 5 is equal to
5. Just 5?
Meters per second. 1.2 over 10.
So we're plugging in our conditions. Okay, so if we solve through this, now to be honest, I mean AP, they're not going to grade you for your algebra. They're not, right?
We never plugged in the C. We have to.
No, I have not plugged in the C. We're solving for the C,
Oh, okay.
right? That's what we're looking.
But yeah.
Now, and this is really important, that 5 meters per second, that's not c, right? That's not c. That's the velocity when we're at 1 second. When we plug in 1 second here in that t, that's what we end up getting here for the velocity. So they're not grading you for your algebra. So you can write down all of your work if you want. Be very, very careful with it. I'm not going to bother writing my algebra. I'm just going to say, okay, therefore, C equals, what did you end up getting?
Like right now you're solving for C, but that's not like what they're asking.
No, that's not what I'm asking for, but I do want to have, I need to find C. I need it. Okay. What did you say, 8.8?
Yeah. And then
8.8 what? I do need my units.
meters
Should it be in meters?
per second.
Should probably be in meters per second, because everything on the left-hand side is in meters per second. It's a velocity. Everything on the right-hand side, therefore, has to be the same thing. What does this C represent?
Wait, hold on. It's 1.2 meters per second squared, isn't it? Not cubed.
Wasn't that alpha?
Oh wait, no, you're right.
Oh, one thing that I did forget. Yeah, you're right. Oh, this should be here, and this should be here. My bad. So, that's fine.
Yeah,
Okay.
Wait, so the units are seconds squared.
The units should be meters per second.
Meters per second. Okay, they did cancel out.
Yeah, they should.
Yeah,
Okay. What does that C represent?
wait, I
that's
don't
a shift.
understand why it's cubed.
Why, what is cubed?
Okay, they tell you what's it called?
They tell me alpha. They give me what that
Alpha is meters per second cubed, but the acceleration
should be meters per second squared.
squared.
Yes.
So why are you plugging cube? How do you know that?
Why did I plug what in? This
Oh, okay.
this is
That
alpha,
and
right?
The t.
Here I wrote a of xt.
Okay.
That was the whole function. This I wrote that,
Yeah, right.
and that whole thing is alpha t. I just didn't write alpha t. Well, actually, here I wrote alpha t squared over 2. I didn't write what alpha was.
Can you write
Actually, here I wrote what alpha was. 1.2 meters per second cubed. There I wrote what alpha was.
Can you write like 1.2 over 2 times 1 and then like write a parenthesis and then put meters per second squared instead of writing it individually?
I think they will let you, probably. I think that's what the unit's reduced to. I wouldn't personally. I think they will let you, if you want. Okay. But no one's answered my question yet. What does C represent?
Oh, the initial velocity.
The initial velocity. That is the velocity when t equals 0. That's how fast the bus was moving when we first started looking at it. That's what this thing is. They didn't ask us for that, whatever, but it is useful to know. This represents v of x 0, my initial velocity. When you're only good at math in your math class, you're not very good at math. And being able to read these things and have that sense about what this means is a really useful tool. And that's one of those things that we're building, one of those skills that we're sharpening. Okay, so now that we've got this function that we can build, so Vx of t is okay, so there's my function.
V of 2 is equal to
What did you say?
11.
11.2 meters per second. Got real fast, real quick. But that makes some sense. I mean, it's accelerating. I guess it had a decently quick rate. And, I mean, it started going at a decent rate.
If the bus positions of 6 meters, what is the position of 2? Okay, so do the same thing, right? To V. Integrate V and then use the initial condition. To find
No, you
C.
already integrated V. You just have to plug in C.
meant to find the position. Integrate d.
I just have one question, Gabby. How did you?
Oh, what's the position?
Is this negative?
Where'd you get?
Why would it be negative?
Wait. So, how did you get 8.8 for C?
I multiplied times 2, which is 10, and then I subtracted 1.2. So 10 minus 1.2.
So that'd be negative.
What?
Wait.
5 minus 1. 10 minus 1.2.
Wait. 1.2 divided by 2, okay, is 0.6. So 5 equals 0.6 plus C. So then subtract 0.6. C should be 4.4.
Oh, because. Oh my gosh. I
Okay.
multiplied times 2, but I didn't multiply the 2C, okay, and then divide by 2.
Okay, cool.
So 8.8
Yeah.
divided by 2.
Oh.
I like did in my head fast.
That makes, okay.
It did 4.4.
It should be 4.4. There we go. You have to take a second, because that 11, that
Oh, okay.
11 does not make any sense.
Okay, so now it's
If
2.4.
at 1 second it's 5, how did it slow down and then speed up?
Yeah.
That
okay.
function, the shape of the function doesn't make sense. Okay.
Wait, it's 6.4.
So this should be 4.4. There we go. Now this makes more sense because it's constantly speeding up. And then
It's
6.8. There we go. That makes much more sense. All right. Okay, so there's part A. If the bus's position at time t equals 1 second is 6 meters, what is its position at time t equals 2 seconds? We're going to do something very similar. Now that we have a velocity graph here, actually, you know what I'm going to do? I'm going to rewrite this over here. Okay. How do I find a position function? Yeah, I'm going to integrate this velocity function. This looks like a y. That should be an x.
Wait, do we plug in C to the velocity? Do we put the velocity function when we're integrating?
Plug in what c?
The one from B.
We know that number now.
Yeah, so now we put it
Yeah.
in. All right.
It's not an unknown now. It's not just any number. It's a very specific number now. We now have a particular solution for our velocity function. This is a family of solutions. This could be any quadratic set of functions, but now we have a particular quadratic that matches this function. All right, so let's take, that'll be the integral of, actually, I'm just going to go ahead and take 1.2 divided by 2 is what, 0.6? 1.2 divided by 2 is 0.6
Oh, yeah.
meters per second squared, t squared.
What?
Half of 1.2 is 0.6, right?
Yeah, but you raised 1 and then divide by 3.
I'm just writing the integral.
Oh, you're writing it in.
You're writing it. Plus 4.4 meters per second, right, dt, right, equals. Okay, now, what do I get when I take this integral?
Oh, you didn't take it in.
No, I have not taken it yet.
T cubed over 5 plus 4.4t.
T cubed over 5.
It's
What?
1.2 t cubed over 6, but 1.2 over 6 is 1 over 5.
So wait, so let's forget about that coefficient in front. So it'll be t cubed over 3, right?
Times 2 because of the bottom. Like 3 times 1.
Well, I don't have a 2 in my bottom. So it'll be
Oh.
t cubed over 3, and then 0.6 over 3 will be 0.2, right?
Yeah, 0.2, which is 1 over 5.
Okay, I like that. 1/5. I like that, the fractions. Meters per second. Oh, I wrote meters per second squared. That should not be it. It should be meters per second cubed. Meters per second cubed, t cubed. Okay. plus, here, what will I end up getting? 4.4 meters per second t.
Wait, how'd you get 1/5?
Because it's 1.2 over, there's a 2 and then 3, and 1.2 over 6 is 0.2, which is.
Oh, so you already
She
did
just converted
that.
0.2.
I keep everything in the fraction form.
Fraction or decimal?
Fraction.
That's fine.
Like, I don't ever until the end.
Oh, yeah, that's fine.
Yeah.
Not a big deal. Okay, and then what do I have at the end?
C is equal to.
Okay, plus C.
And then
Okay, then I got to do my initial condition. Hold on. Let's switch over. Okay, so let's rewrite that function real fast. So x of t is 1/5 meters per second cubed, t cubed, plus 4.4 meters per second t plus c. Okay, so then x at what? Let's double check real fast. X at 1 is 6. X at 1 second is 6 meters. Well, let's plug in real fast. You said 1.4? So that's 1/5 meters, 0.2, 4.6. What does this represent? The initial position of the bus. Okay, and then they asked us to find what is the position at time t equals 2. And x at 2 seconds. Actually, you know what I'm going to do instead? I'm going to just rewrite the function. So then x of t and then x at 2 seconds is, let's see, 2 cubed is 8. 8 times 1/5 is 8 over 5, which is, what?
1.6.
That's the total, or? Okay, so 1.6,
4,
which is 6.
would be 8.8
Oh,
plus
yeah.
1.6 plus 1.4, which is 11.8.
Okay. That's not bad. David, you got the same thing?
I did not get an answer yet.
I'll give you, I'll wait 1 second.
I kind of fell behind because I didn't get the answer, so it's fine. But I understood what you did. Yeah, I'm still solving for C.
I don't mind waiting.
Where are you solving for? Oh.
In fact, we can double check too if you want.
Yeah, you can't just. Would you do this with? You have a calculator, right? Yeah.
You're allowed to calculate the whole exam. It's not like calculus.
Oh, it's completely. Oh, cool.
A lot of the times, especially on the multiple choice portion of the exam, a lot of the calculus stuff that you'll get will be things like this. Here is a velocity function. Find its position at this point. Here's an acceleration function. Find its displacement and its velocity, stuff like that. So it's about identifying that what you should be doing is taking things like integrals and derivatives and figuring out the limits of integration, or the other common thing is they'll give you a graph and trying to figure out if you should be taking areas or slopes. Now the last part of this question is my favorite part of this question. And it says, sketch an acceleration versus time, a velocity versus time, and an acceleration versus, a position versus time for the bus. don't want to give nothing away. Okay. So where do you think is the easiest place to start?
Probably acceleration,
Why?
Yeah, because we already know.
linear, and shift.
Yeah.
Yeah.
Is linear, and the linear stuff is easy to start with.
Yeah.
So, what should I draw? Where should I be?
Has a slope of 1.2 and no.
That's true.
no axis. Like that is 0.
Where should I start?
Level line.
What does it start at?
0. 0, 0. No,
Starts at 0, 0. Okay. Which way does it go?
up to the right. Entering 1.2.
Yeah. And then V.
Yeah.
If you want, you could do something like if you want.
I mean, M is sort of reserved for maths, so.
No, but it's a graph and it's linear, so they know that m means slope. You could do something like that if you wanted, but if it says sketch, then they're not looking for values. They're not looking for that. They just want to know, do you understand what the shapes should be? So they're looking for trends, right? And they're looking, like, for example, do you understand that this thing is positive? Do you know that it does not have an intercept anywhere except 0? It does not cross the x-axis, right? That's important.
Yeah.
Definitely is continuous. The velocity graph. Here, this one's also important. Sketch,
Yeah,
but it is quadratic, number one, but it does not start at 0.
Yeah.
That's important. Even though it does say sketch, it's really important to know that it doesn't start at 0. It starts at
4.4.
4.4.
Yeah.
Starts up, right? So starts somewhere up here, and it goes up. That's important. So they're going to look for, do you know that it starts up here and it gets bigger? That's really important. Really thirsty.
Last one is the cube.
Now, these ones are a little tricky. What you could do is something like y is proportional to squared. So you can imply that this thing is a quadratic, right?
Yeah.
Especially since if you're only showing the first quadrant, quadratics and cubics are very, 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 very similar, right? If you're only looking at the first quadrant and you're sketching, you're not showing values, they're very hard to distinguish between the two because, like, they get big real fast. You know what I'm saying?
Yeah.
Big picture, quadratics and cubics really distinguish themselves when you can see
Both sides.
both sides, right? But this guy,
Same thing.
very similar, right? They don't start at 0. Where does this guy start at?
This guy has a C value.
1.4. So you could probably distinguish it a little bit by not starting quite as high. It starts a little bit lower, right? 1.4 is a little bit smaller than 4.4. You could also probably make it even sharper up if you really want to make a big distinguisher. Or you could say something like, it's proportional to x cubed. You could,
Alpha is proportional.
yeah, that's the proportionality symbol in general. So you could say something that looks like that. Just to really highlight and say, hey man, like I understand these look very similar, but I want you to know this guy is definitely cubic, this guy is definitely quadratic.
But the first one is y is proportional to alpha.
No, you could say something like y is proportional to x.
Got it.
Yeah. Because y is proportional to alpha would be a horizontal line, right? Because it's proportional to a constant.
Yeah.
So these graphs are really important. Don't forget the graphs. Graphing these things are so critical. And foreshadowing. Not this one yet, but it will be. It will be. Well, we are going to graph, but still. All ready? Oh, okay, I guess already. Okay. A student, this is that challenge problem. I don't think it's super, super challenging. To be fair, this was on my final. No, this was not my final. This was on my partner test when I was in college in my modeling class for physics. We had a partner test. This was question 2 on my partner test. Or something very much like this was question 2 on my partner test. Ever since then, I really have a love-hate relationship with it. I enjoy this question. It makes me very upset that I did not know how to solve it at the time. I felt like an idiot, and I don't like feeling like an idiot. So a student is running at her top speed of 5 meters per second to catch a bus. You're noticing a trend. Physics doesn't like buses. Which is stopped at the bus stop. When the student is still 40 meters from the bus, it starts to pull away, moving with a constant acceleration of 0.170 meters per second squared. Okay, so you guys get? Yeah. Oh, you mean like you want to set up a function and let's not do that. All right, because don't do that. Because okay, yes, on the exam you can. Let's not do that now. All right, I want you to go through the motions of how to do that. I want you to think about the thinking, and then after it's not that bad. Okay. Thinking about thinking is one of the most useful things you can ever do. Like, it is introspection. If you learn anything in life, learn introspection. Introspection and meditation are two very useful things, and they're things that I'm trying to get better at. Introspection, I'm good at. Meditation, I'm terrible at. But I recommend it, man. I recommend it. Okay, so you guys understand the picture that's going on? So the bus was stationary, students trying to catch up, students still behind, bus is accelerating from rest. For how much time and what distance does the student have to run at 5 meters per second before she overtakes the bus? Now, this is a weird wording. Okay, so this is weird wording. Overtakes the bus. What that really means is catches up to the bus. You can't overtake the bus until you get to the bus. You know what I'm saying? For some people, that was the number one biggest. I put this on an exam the last 3 years, and that's the number one biggest thing that people struggle with. They just don't know what that means. So they're like, what? So,
what else is there to do?
You would think. I thought. Well, I'm just saying. Okay, so let's start with that first, and then we'll deal with it. So, what do you think we gotta do?
Wait, what time and what distance?
Yes.
Wait, I don't understand something. It says a student running at her top speed to catch. So when the student is still 40. Okay, like when she is 40 meters, she's still at 5.
Yes, the whole time the student's running at that speed.
The bus is stopped and then it starts moving.
Yes.
Yeah, so the bus is like, oh wait.
So
at the instant the bus is stopped, but the bus starts moving instantly.
Yes. So a couple things that could be useful. Number one, picture.
Yeah. So
could be useful.
Position versus time is going to be our what?
Let's draw two pictures then.
Graph or picture?
Let's draw two pictures then. Let's do like a picture, and let's do a position versus time graph. All right? Let's start with a picture, and then let's do a position versus time graph. How about that? Okay. So our picture is going to be very basic. How about very small bus. Student. Terrible arrow. I'll call that velocity S, so velocity of student. Now, here's where we need to be a little bit careful. We got some freedom, but that freedom, if we're not careful with it, could bite us in the butt. They never gave us our reference frame.
Yeah.
They never told us where that was. They told us that there's 40 meters. You want to make it the bus? Okay, that's fine.
Oh wait, I made it.
You made it the person?
Yeah.
Whichever one you want.
Yeah, I like the person though.
Person, okay.
Wait, that confuses me though, because it says that it's 40 meters from the bus. So my reference was the bus, so I made it minus 40, like
I made the bus
15
40.
minus 40.
I made the bus plus 40.
Oh, because you didn't make the bus.
It's just I like positive numbers.
Okay, fine. Here,
So what do you want to be? Person?
Yeah, sure.
Okay. So the person is going to be 0. all that's going to change when time stops being 0, right? As soon as time starts flowing, things are going to start changing. But that's okay. So the person's going to be 0, which means the bus here is going to be 40. Let's see. What else do I need? Okay, I'll do it in red. The velocity of the bus initial is 0. The acceleration of the bus is 0.170 meters per second squared. I think that's all the variables that were given, right? Yeah, okay. So there's my picture. In terms of position versus time graphs, well, actually, if the person is 0, then everything is positive, right? Okay, so then maybe I don't need that. Maybe I can just do this.
Wait, how many decimals did you say?
You could put 0.17. They did 0.170, so that they know so that you know you should use 3 significant digits, but that's fine.
Wait, I forgot the rule for significant. It's the least. Right?
You can never be more accurate than your least accurate number. They honestly, on the AP exam, they don't care about significant figures. Usually, they don't want you to use more than 3 decimal places.
Okay, so
I just always use 2 because they don't care.
Because I use 2 for
Yeah, I usually never use more than 2.
I mean, in
As
Chicago,
a-
people don't know, use more than 2 decimals. So
I usually never use more than 2, but okay. So for the person, they are at what position at time t equals 0? 0. And what is the shape of their position versus time graph? Linear. Okay. So there's a good chance that their position versus time graph might look like this. All right. Okay. For the bus, actually, you know what I'm going to do? I'm going to label this x of t of the person. Okay. For the bus, they are not at 0. They are at 40, and their position versus time graph will be what?
what's the question?
What shape will the position versus time graph? Not exponential.
Was it
No,
not?
it would be.
No, it can't be exponential.
I mean, quadratic.
Quadratic. It'll be quadratic, so it'll look maybe, and then it won't start at 0. It'll start at
40.
40. It'll start up here at 40, and then it'll be quadratic, or yeah.
Twice, right?
It could intersect twice. So there's a good chance it'll intersect twice.
Unless it's a tangent line.
Could be. Actually, that's part of the question. We'll see in a second. Oh, actually, they did tell us take x to be the initial position of the student. I didn't finish reading yet, so that was nice for them. So there's a really good chance they will intersect. They have to intersect, hopefully. So
Unless it's tangent.
yeah. Well, actually, if the slope of the rise of the quadratic is steep enough and the slope of the linear is shallow enough, they will never intersect. But
Yeah.
okay, so now I've drawn these pictures, which are very useful. What is the key to this? What's the next step that I should do?
Systems of equations.
That's true, but in order to have a system of equations, I need equations.
You need it to write.
So I need equations of motion. Okay? So my equations of motions are going to come from the equations of their positions. I'm going to write an equation of position for the person. Yeah, they call it a girl. I'm calling it person. Whatever. Doesn't matter. Runner, girl, whatever you want. Okay, so the person starts at position 0. So x naught is 0. Their initial velocity is 5 meters per second times time plus 1/2 a, but their acceleration is 0, t squared, that goes to 0. Okay, so there is their equation of motion. That's not super great, but whatever. Okay, that's there.
Velocity is 5 meters per second.
Yeah.
Oh, that was then
And
just
acceleration is
And their acceleration is 0. Next is the bus. Okay, the bus, so x of t of the bus, their initial position, x naught, is 40. Plus v naught t but their initial velocity is 0, so that goes away, plus 1/2 a, their initial acceleration, or their acceleration is 0.170 meters per second squared, t squared. Okay, so I've got these two equations of motion.
Wait, so that. Oh, alright, that's one way. I used plus c and replaced plus c with 0 for the first one. Like, how come you don't have a single integral? So how did you do it?
A single integral?
What?
You didn't integrate.
I'm not integrating anything. I'm taking I know what the equations. Remember that from kinematics we derived these, right?
You can also just
I did it, yeah. I integrated velocity for each.
Oh yeah, okay. If you want to integrate velocity, where'd you get their velocity functions?
I'm manually doing it.
If you want to integrate the velocity functions, you can.
It's a bad
It
idea.
doesn't take long. You know that it's super.
No, for the girl it's easy. For the bus it's an acceleration, so you take the second order integral.
Yeah, you can do that.
It's gonna be a bit of a-
It's not terrible. It's not terrible. But this is why we did all of this work in the beginning of the semester.
Yeah.
We derived these in the beginning of the semester. We might as well use them, right? Not start back from 0.
But integrating is always easy because the acceleration is constant.
It's always up to you if you want. So if I want to know when they will be in the same place, what do I have to do with these two?
You equal the positions.
I'm going to set them equal to each other. So for the bus, what's half of 17?
What is it?
0.085. And you'll notice that this is going to end up being a quadratic, which makes sense.
What do you mean? But we should probably pick it first, right?
Give me 1 second to finish writing this out. Okay, all right, there we go. So I have really, I guess technically, two options here. I can pray that this thing is factorable, or I can really just do the quadratic to this thing. If you got a fancy calculator, you can throw this in and say solve. Doesn't matter.
Randomly. I have to write down like the program.
Oh,
'Cause
yeah.
It doesn't come with it, so
It doesn't?
no.
Oh, I could have sworn it did.
Mine
The
does.
solve comes with.
The TI-84? I don't know. I don't know how. I literally just plug it into the quadratic if I have to. If you plug it into the quadratic, you'll get two solutions. So you'll get t equals, what did you get? 9 point what? 55. Or
49.2.
you'll get two solutions. We will hold on to that for 1 second. So that's part of the question. Over what time? Now, the second part of that question says, over what distance? So we can go back to the equations of motion, and does it matter which one we pick?
Where does it say this?
Well, if we look through here, it says for how much time and what distance.
Oh, okay, so just tell me back then.
Does it matter which one we pick? No, because they're at the same place. Now, one of them actually will end up being 40 more than the other, right?
What?
One of them should be 40 more than the other.
What do you mean 40 more?
Well, the girl is 40 behind.
Yeah, but she catches up.
She does catch up, so she's going to run 40 more,
Okay. Oh, okay. She's running. Yeah. Oh, okay. The position should be 40 more.
right?
Wait, are those
So,
two sets
for-
equal?
They're the same position.
They're in the same position, but the question says over what distance does the student have to run?
Oh.
So we figure out what position they're at, and we just add the 40. Does that make sense? Right? So let's plug that into the student's function. That should include the 40.
Wait, we're still doing A, right?
Yes, yes. The reason why I should include the 40 is because we set the 0 to be where the student is. Does that make sense?
But if the buzz was 0,
Then we would end up having to add 40. If we plugged into the bus. If we plugged into the bus.
Wouldn't you have to add 80?
Because the student is...
Like if the buzz was 0, your equation for the girl would be 5 meters per second t minus 40.
Mm-hmm.
And then...
But it depends on which function you're plugging into. Because if you plug into the bus's function, then you're going to end up having to...
Oh, then add 40.
Yeah. If you plug into the girl's function, then you won't have to, do anything.
Okay. But why would you plug into the bus if they're asking for the girl?
In math, usually, it doesn't matter what you plug into, right? So a lot of the times people use those habits.
Okay.
Here, it does matter because we're being asked something very specific.
Mm-hmm.
But it's just about keeping track of things. David, here they're asking us for how much time and what distance. We just found the times.
Oh, you already knew the time, and you're just plugging back in.
Now that we've got these times, and the thing is it's quadratic, so there's going to be 2 times. Previously, when we were doing quadratic things, very often, we threw away one of the times because they ended up being negative, very often.
But in this case, we want the first one.
Oh, yeah, we want the first one, and the first one makes more sense, right? But I'm not going to throw away either one of these times, actually. Not yet. I'm not going to do it yet.
Why would you throw away the second one, the last one?
I'm just not going to do it yet. Mostly because I know there's a second part to this question. So, but you'll so let's plug in that first value, 9.5, into the girl's function here. So 9.5 times 5 is going to be a little bit more than 45, right?
47.7.
Okay, so x of 9.55 seconds for the girl is 47 point what? 75 meters. So the girl has to run 47.75 meters. So not only does she have to run the 40 meters as she's behind the bus, but then it's going to take her another almost 8 meters, to catch up to the bus. That's not too bad, right? You've caught up with us, David, or you're almost there?
Almost. I just wrote down the thing. Let me just write down those 2 numbers. Which gives us.
Before we go to lunch, I just want to take a look at the second part.
You just plug in 9.55 into the velocity bus.
Okay, so the equations that we use in part A to find the time intervals have a second solution. Of course they do, because they're quadratics, and in general, quadratics have either 0 solutions, 1 solution, or 2 solutions in general. Corresponding to a later time, because that number is bigger and positive, for which the student and the bus are again at the same place if they continue their specified motion. Explain the significance of this solution. What does it mean?
The bus, okay, she catches up,
And the bus catches back up with her.
Yeah.
So actually, if we would have drawn this picture a little bit better, this is probably what it would look like. I'm going to blow this up a little bit. This is her picture. The bus's picture actually looks a little bit more like this.
Yeah. Well, not going downwards.
Well, yeah, you know what I mean. Something like that. So she's actually going fast enough where she's going to actually blow past the bus, right? And then the bus catches up again to her afterwards. And the bus is actually going so slow that it'll catch up to her 40 seconds after the first time, which is pretty slow, actually. The bus is going pretty slow. So that's not bad. How fast is the bus traveling at this point? Well, we have an equation.
Stop once she gets to the bus.
What?
When she
Ideally, yeah, but I mean, physics problems don't have to stop when we're... Have you heard, you know who Louis C.K. is, right? He's a comedian. He's a comedian, whatever. He's got this skit about food and dinner, and he's like, the meal isn't over when I'm full, all right? The meal is over when I hate myself. And that's very true. Physics isn't over when we've answered the question. Physics is over when we hate ourselves, and we're like, ah! So... we have an equation for the position of the bus. We could, if we really wanted to, we could take the derivative of this guy and find an equation for the velocity of the bus at any point. We could. And then we could just plug, oh, wrong way. We could plug,
We already have that.
well, you already have that because you started at the acceleration function and then integrated up. I started with the position function that we derived at the beginning of the year, and then I'm going to work my way down. So it's up to you. Then we can plug in that number and find the velocity. What was the next? Oh, wrong way again. What was the next thing it asks us to find? If the student's top speed is 3.5 meters per second, will she catch the bus? So remember how we said, remember what we said, if that function is shallow enough, will she catch the bus? What is the minimum speed to catch the bus? And then that tangent line, I get there at that 1 point.
Yeah.
So we can pick up at point E tomorrow.
That sounds really cool.
Yeah, F is the one I really want to do. We'll start with that tomorrow.